So I'll begin with a word of prayer. Heavenly Father, we thank you for this morning. I thank you again for these students, for the break. And I just pray you be with us today. Help us to glorify you in what we do. Again, I pray for these students that each day that they would, just as they work on this course, that they would be encouraged just to do their best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so I guess we're probably supposed to top that, right? Any questions about the participation assignment while I'm getting my computer to wake up? So just to tell you, the thing that's due Thursday, right? It's not complicated. You just need to watch the videos I posted Wednesday before break, right? And it's best for you if you work through those examples of long division, right? But technically speaking, to get full credit on the assignment, all you have to do is watch the videos and see the answers to each. So I have, basically write the conclusion of each example. There are like 10 examples. So you just record the conclusions on the participation sheet, and then you turn it into me Thursday. All right? So that's all there is to that. It's not, really shouldn't be that complicated, but the point of that was just to give you a large and, if I had done those examples, by hand in class, from scratch, it would have taken probably 3 classes, right? Just because it takes a fair amount of time to carefully go through a long division. But those examples are good examples for you to practice on, if nothing else, right? So do keep them in mind for that. You're like, but what about the top hat? We haven't lived until we've top hatted today, right? Let's see here. So you guys are section 4, I think. Yeah. 9138. All right. So today, I'm going to talk about a couple different things, all right? First of all, if there are any questions, feel free to ask. But actually, you can ask questions at any point in the lecture, right? But anyway, today we're going to talk about, at least to start with, reverse problems, all right? So what do I mean by that? So here's sort of the generic format is we're given some data about a polynomial, then we're asked to create or construct such a polynomial. All right. So this is backwards of the problems we've worked up to this point, because up to this point we've pretty much had problems like, I give you, here's a formula, right? And then find its graph, So here I'm going to go the other way around. I'm just like, here's a graph, or here's some data. Let's figure out a formula which will reproduce those features. All right, so example 1. So example 1 here, I'm going to give us a graph, and it's going to have some points on it. All right, so here's the graph. So here is the graph of some polynomial, all right? And I'm going to tell you that this intercept right here is at -9. This intercept is at -1. The y-intercept, I'll leave that one in a second later. This other x-intercept is at, let's say, 2. And this intercept over here is, let's say, it's 7. All right? And let's suppose that the y-intercept is 126. So obviously my scale is not quite the same for the x and the y-axis, right? So the question then is, can you construct a polynomial which looks like this? What would the formula for such a thing be, right? So I'm going to build the first one. Just dive straight into it here. So what I want is something like f of x. So first of all, I put an a for being able to adjust the height, basically, okay? So just constant out front, a. To get this minus 9x intercept, I just put an x plus 9. That picks up the first x-intercept. To pick up this minus 1, I put an x plus 1. But that won't do it, because at minus 1 rather here, it's bouncing, all right? So if it bounces, what you want to do is put a square. So x plus 1 squared. Then we're crossing at 2, so I put an x minus 2. And then finally we cross again at 7, so I put x minus 7. That should do it. That will give me something that bounces at minus 1. It crosses at minus 9, 2, and 7. Like that. All right. What's the order of this polynomial? 1 plus 2 is 3, plus 1 is 4, plus 1 is 5. It's a 5th degree polynomial. That makes sense. This is kind of like that kind of thing, right? A 5th degree polynomial. We expect that a is going to be what? Positive or negative? I expect it's going to be positive. Wait a minute. Oh, it's going to be, well, it's going to be positive, right? Because it kind of generically speaking looks like that. All right, so how do we figure out what a is? Well, there's one thing we haven't used yet, right? This 126. So what is 126? This means what? This means that f of 0 is 126, right? So I put 126 equals f of 0, which is a times what? Plugging 0 into this formula gives me 9 times 1 squared times minus 2 times minus 7. So 9 times 7 is 63. 63 times 2 is 126. So what we have is 126 equals a times 126. Notice the minuses cancel. So we get a equal to 1, right? So you can almost assuredly be sure that a will not work out to 1 on your next quiz or test, because that would be very poor planning on my part. You know, how do you grade quizzes and tests on this kind of problem if you have your constant come out to 1? You can't tell the difference between a student who checked and found the right a versus one who just ignored the issue of needing to put an a there in the front, you know? So that would be a bad example. But anyway, this is nice. A is equal to 1. So the answer is f of x equal to x plus 9, x plus 1 squared, x minus 2, x minus 7. There you go. That's it. That's the answer. All right. Example 2. And, oh, I forgot the instructions here. My bad. Well, let me put the instructions in example 2. Find polynomial f of x of least degree which has the following graph. All right, so do something like this. And we'll make this point be on the graph here. This point will be two comma minus, oh, I don't know, 40. So that, the instructions for the first one were find the polynomial, you're fine. Polynomial of least degree, which, you know, has a graph that looks like that now. So here's another one. So you guys help me out with this one. This one's a little different, right? I didn't give us, this time I did not give us a, you know, what's the word? A y-intercept, right? I gave us the point 2 comma minus 40 on the graph. That's a little different, right? Okay, so how do we deal with this one? You guys help me out. F of x equals to what? What should I do here? Start out with an a to adjust the height, yeah. So how about this x, this minus 5? How do I adjust the formula for that? You guys tell me. X plus 5? What do you guys think? Are we done with that? Does it need to be modified a little bit? We have to square it because there's we're bouncing there. We're bouncing off the x-axis, so square that. Likewise, x plus 2, same story. We have to square that one, right? How about the 1? How do we get the 1 in on the graph, which we put in our formula? By the factor theorem, we should put x minus 1, right? All right, now what's the final piece in the puzzle here? X minus 6, very good. Okay. Now then what? So what else do we know? We know that 2 comma minus 40 is on the graph. What does that tell you? This right here, right? This means that f of 2 is equal to minus 40. Okay? So how do we use that? Well, we set minus 40 equal to f of 2, right? So let's do it. F of 2, well, let's see, minus 40 equals to f of 2. But what is f of 2 equal to? It's equal to a times 2 plus 5 squared, right? What's 2 plus 5? 7, right? So 7 squared. 2 plus 2 is 4. Square that. 2 minus 1. 2 minus 1 is 1. 2 minus 6 is minus 4. Right? So I've got that number to deal with. I came prepared today. Yesterday I was a victim of my children's thieving of my calculator. I had to calculate horrible numbers yesterday. I had to think. No thinking today. Let's see here. 7 squared times 4 squared times minus 4. That is minus 3136. And then, of course, well, I mean, let me not be dumb about this. Oh, it's too late. I've been dumb. So a is equal to, I mean, you could cancel numbers on both sides and make the arithmetic a little bit easier, but I'll just do it this way. Minus 40 divided by minus 3136. What does that work out to? Five over 392. There you go. All right. And so what's the answer? The answer is f of x equal to 5 over 392 times x plus 5 squared times x plus 2 squared times x minus 1 times x minus 6. There's your answer. I think this one's dead. Any questions? Yep. I plug in 2, so put in, going from here to here, set x equal to 2. No, that's fine. So, yep. Other questions? Good question. So here's another example. This one's going to look a little bit different. Example 3. Find polynomial f of x with x-intercepts of, let's say, -4, 0, 3, 0, and, I don't know, 6, 0, with 1, 10 on its graph. Given that f of x is greater than or equal to 0 for all x. So this one's a little bit more challenging in the sense that I didn't give you a picture, and I'm trying to make us think a little bit. Like, how can we make this happen? So the picture is part of the solution, right? It's not given. We're going to have to kind of think through it. We got x-intercepts at -4, right? At 3, 0, and at 6, 0, right? We know that the point 1, 10, let's say here, is on the graph, right? What else do we know? We also know that the polynomial is non-negative, right? Which is to say it's either positive or 0, the values of the function, right? So what does that tell us? What? I'm going to start building it. You guys tell me what I have to do here. I guess let me ask a more pointed question. Can the graph cross the x-axis? It cannot, right? So what does it have to do? Every x-intercept, it's got to bounce, right? So it forces you to do what? Something like it's got to look something like that, right? Now I forgot, I should also have said polynomial blah 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 for all x. I meant to say of least degree, okay? Otherwise the problem is ambiguous, because you could always make it look kind of like that using, instead of squares, like 4th powers or 6th powers or 8th powers or whatever. So we do x plus 4 squared, x minus 3 squared, and x minus 6 squared. Yeah? Just like that, and that should do it for us. Now this point here was 110, right? And so that means what? That means that f of 1 is equal to what? 10 is equal to f of 1. So if we plug in 1 into the formula, what do we get? We get a times 5 squared times minus 2 squared times minus 5 squared. So if you look at that, we can rewrite this as, well, I mean, you could cancel some numbers here, right? But let me resist the urge to do that, since I'll just solve for a. A is equal to 10 over, well, the minuses go away, right? So we've got 10 over 5 to the power 4 and 2 squared, right? 10 is what? 10 is 5 times 2, right? So if you want to do the arithmetic like this, you can. We get 1 over 5 to the power 3 times 2. And of course you could just use your calculator to figure this out, but it's 1 over 250, right? So here we go, f of x equal to 1 over 250 x plus 4 squared, x minus 3 squared, x minus 6 squared. Okay, so there you go, that's the answer to this problem. All right, at this point, I need to make a public service announcement. So some of you, when you encounter this problem on the next quiz or test, what you're going to do, for reasons I don't completely understand, but I believe this will be true of you because it was true of your predecessors. You will feel the need, some sort of internal urge, I don't know exactly how to say it, but something will drive you to try to multiply these out. You will multiply these out. You'll multiply this out. It will take you 20 minutes of work to just multiply these things out. I didn't ask you to multiply them out, right? So like, I don't want us to multiply these out unless I ask for it, okay? If I want you to multiply the answer out, I wouldn't just say find the formula for f of x. I would say find the formula for f of x in quote-unquote standard form. Standard form means, like we wrote last, a n x to the n plus da 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 plus a2 squared, a2x squared plus a1x plus a naught. Like when you write it all out as a sum of powers of x times numbers, right? Standard form. We don't have to give our answer in standard form. These are perfectly good answers, right? And I don't want for you to suffer the fate of like wasting your time on the next quiz or test multiplying these things out when you don't need to. So I'm telling you these things now to try to head it off at the pass. So please do not make this comment a self-fulfilling prophecy for you. You know, like I'm trying to make your life easier. You don't have to multiply these ones out. Now in contrast, the example I'm about to work, we're going to need to multiply out. But so to try this on here. Find, well, let's see here, given parabola y equals to f of x has vertex minus 3 comma 7 and 2 comma 10 on its graph. Find formula for f of x in, now I'll add the words, standard form. Okay? So this problem here is not, this is a different kind of problem than we've worked so far today, right? Do you see the big difference here? The big difference is that this one's about a parabola, right? And parabolas are not just any old polynomial, they're special polynomials. We know all kinds of stuff about parabolas, right? Probably a quarter of the formula page for you guys on test 2 should be occupied with formulas for the parabola, right? We know all kinds of stuff for this. So what do you think what's the right tool to pick out of your toolkit to use to work on this problem? What would you want to use that we discussed to do this problem? What's the right starting point? What's that? Graph it? No need. But we could, but there's no need, yeah. That's not a bad idea. Like, if you don't have the other thought I'm searching for, graphing it would be a good thing to do, because graphing it might shake loose the other idea, yeah.
Figure out like a slope, like with a standard form or something.
Well, the right form is the right kind of idea, but we got a vertex, right? So we talked about 3 different forms for the equation for a parabola. Remember, we had the standard form. We don't have enough information to do that. We had the x-intercept form, like a times x minus r1 times x minus r2, right? The intercept form. x-intercept form. And then there was another one, which was the vertex form. Well, we know the vertex here, so vertex form is the one to go with. So vertex form is just this. Y equals to a times x minus h squared plus k. This is definitely something that should be on your formula sheet because it makes a problem like this easy. And it's just also something you want to know. If you have a formula like that, you go, oh, that's a parabola, and the vertex is at h comma k. Now, h comma k is what here? H comma k is equal to, it's given to be minus 3 comma 7, right? So that means my h is minus 3, and my k is equal to 7. So I can put that in to the template, and I've got myself a y is equal to a times x plus 3 squared plus 7. And instead of writing y, I'm going to write f of x, okay? Because that serves my purpose better here. So you have f of x is equal to a times x plus 3 squared plus 7. That's gonna give me a parabola with the vertex minus 3, 7, okay? Now there are infinitely many parabolas like that, but there's only one that also has the point 2 comma 10 on its graph. And so if we'd done, what was your name? Say again? If you don't, Iwana said, sorry, I've mispronounced your name, but if we did what she said and graphed it, then you'd kind of be able to see it, that there's only one answer, right? But we don't need to graph, is the larger point, because we can just plug in, what does this 210 mean? This means, so 210, an element of the graph of f of x means that f of 2 is equal to 10, right? F of 2 is equal to 10, and let's do that. So 10 is equal to f of 2, but what's that? That is a times 2 plus 3 quantity squared plus 7. That's one equation and one unknown. You can solve that all day long, right? It's not a problem, hopefully. I think that's true for everybody here. So subtract 7 from both sides. We get 3 is equal to a times 5 squared, which is 25. So we get a is equal to 3 over 25, which then tells me my answer, y is equal to, oh, excuse me, is this the answer? 3/25 times x. I hate writing down here. I'm going to, if you don't mind, I'm going to move up a bit, because my writing down at this level of the board gets kind of bad. I'm going to stick the answer up here. So we get f of x, and again, this is not quite the answer, 3/25 x plus 3 squared, all right, plus 7. Why is this not the answer? What would the question ask for? Standard form, right? So what do we got to do? We got to do that thing that I've been encouraging you not to do for the previous 3 examples, right? Like multiply it out. So 3/25. How do you multiply out x plus 3 squared? That multiplies out to what? X squared plus 6x plus 9, right? So we FOIL out x plus 3 squared, we get x squared plus 6x plus 9. I'm going to repeat that. When we multiply out x plus 3 by itself, right, we get x squared plus 3x plus 3x plus 9. The 3x's combined to give you 6x. That's why we get x squared plus 6x plus 9 here, right? We all on the same page? So then we add 7. Now, of course, now I need to multiply this fraction through, right? So that gives me 3/25 x squared. 3 times 6 is 18, so 18/25 x. And then 3 times 9 is 27 25ths plus 7, right? What is 27 25ths plus 7? That, well, you can get your calculator out, but 27 over 25 plus 7 is equal to 27 plus 175 over 25, which is 202 over 25. So the answer is 3/25 x squared plus 18 over 25 x plus 202 over 25. There you go. There's the polynomial in standard form with simplified coefficients. We good? I hope. All right, so what comes up next in here, guys, is another, so now we're turning the page here. So you guys can, there's homeworks on these, right? You should try to work them out. And if you get stuck on the problems about graphing polynomials and everything, you come to the next classes, ask me questions about them, right? It's all good. But we are now going to move on to the next sort of problem, well, set of problems, which is graphing rational functions. All right, so we need to talk about how do you graph a rational function. Before I get into that, though, are there any more questions about this material this morning? Okay, so let's talk about graphing rational functions. Now, the first question is, what is a rational function, right? What is a rational function? So if f of x is equal to p of x over q of x, where p of x and q of x are polynomials, then f of x is rational function. All right. So a polynomial divided by another polynomial, that is a rational expression. A function whose formula is a rational expression is a rational function. And so let me give you a kind of a sketch, a game plan for how we graph such things, okay? So here's the roadmap for graphing. All right? So step number 1. If the degree of p of x is less than the degree of q of x, all right, then y is essentially equal to 0 for x going to plus or minus infinity. All right. So what I'm saying is, if the degree of the numerator is strictly less than the degree of the denominator, what's going to happen with your graph is eventually it's going to 0. All right? However, if the degree of p of x is greater than or equal to the degree of q of x, then do long division. All right, then you do long division, and you get f of x equals to p of x over q of x, right? And that works out to, by long division, let's give this thing a name. I'll call it g, for lack of imagination, g of x plus the remainder function of x divided by q of x. All right. And then, so just to emphasize what's going on here, the pattern that you're going to see is that this is a polynomial, and this guy right here is what's called a proper rational function. And what I mean by proper rational function is one for which the degree of the numerator is strictly less than the degree of the denominator. So the proper rational function has the rather pleasant feature of going to 0 for x going to plus or minus infinity. So what this all means is that, what this all tells us is that y is approximately g of x for x going to plus or minus infinity. All right, so we have either this case or we have this case. This tells us the large scale behavior of the rational function. All right. Now, oftentimes, for the bulk of the examples I'll ever ask you to work, and will ever work in class, that g of x is at most going to be a number. Right? So a lot of times g of x is just a number, and so we're just talking about a horizontal asymptote. In the case g of x is just a number. Horizontal asymptote, all right? Horizontal asymptote. So that's step number 1. All right, now, oftentimes it's not that complicated, okay? So, because most often we just find ourselves with the first sentence being the logical one, and we're just, okay, great, it goes to 0. Step number 2. You completely factor your p of x and q of x. All right, completely factor them. And notice at step number 2, I'm forgetting about the g of x if there was one. It doesn't really matter what g of x is for what goes past here. We kind of just forget about it until we make the graph for now, okay? So we completely factor p of x and q of x and identify all critical numbers, right? So what's a critical number? Let's be a little bit more specific. Suppose that, let's say, C1, C2, CR are zeros of p of x, and let's say D1, D2, DS are zeros of q of x. So you have zeros of the numerator and you have zeros of the denominator. All right? And then what do you do? Then what you do is you put all of these on a number line. Sorry, I'll write over here. So step 3 is you place C1 C CR and the D1 DS, all the critical numbers on number line. All right, so I don't know how they're arranged. C1, maybe D1 comes next, then there's C2. Who knows, right? It goes on. All right. I probably would have been better just not even to put these on the number line. You don't have to. The point is you arrange them on a number line in order, all right? And then you test points in each subcase and add pluses and minuses, all right? So you add plus minus as appropriate, just like we did in solving the rational inequalities earlier in the course. Same song and dance. Then there's graphing, okay? Graph it. Now, there's some guidance I should give you for the graphing. All right. So in terms of the critical numbers, this is where it gets a little bit interesting. So you look at each critical number. All right, look at each critical number. That's the numbers from the list of zeros for the denominator and the numerator. Okay, so here's the way it works. If the order, let's say, of critical, let's call the critical number C. If the order of C is larger in denominator, which is what, my Q of X, then X equals to C is vertical asymptote. All right? If the order of C is the order of X is C is greater than the numerator, and in the denominator, then 0 is a whole in the graph. Or if there is no factor minus a in 2 of X, stay X. So you watch your letters on right up. Just jump right example. Not just more today. Just want to more you don't want people today. But maybe you have to propose below later. It is over. Like, oh. Yes, make the graph. So you could put off number 1 until later if you wanted to. Like, it's not written in stone, you have to do this first. I was just doing it first so I didn't forget. Okay. Now, because usually what happens is I forget, and then I get to all the way to the end of it, and then I face the music. Okay, so 2, we completely factor. So f of x squared minus 4 over x squared minus 9. Can you factor those? I hope you can. That's x plus 2, x minus 2 over x plus 3, x minus 3. So critical numbers of, x squared minus 4, well, let me say of numerator, more to the point, numerator, are minus 2 and 2, right? Critical numbers of denominator, and more to the point, you could say zeros of the numerator, zeros of the denominator. These are zeros, right? Roots of these polynomials are what? Minus 3 and 3, right? So let me give you a further simplification of the algorithm. So here I'm all worried about when the number is both in the numerator and the denominator. That's where the complication comes from. So oftentimes in examples, there is no overlap of the critical numbers between the numerator and the denominator. Like here, this list and that list, they're distinct, right? In this case, it's really simple. The ones that are in the numerator give you x-intercepts. The ones that are in the denominator, they give you vertical asymptotes. And that's all there is to it. So, what you got to watch out for is when there's an interlinking between these numbers, then you got to sort through it according to this more description of there. So this gives us x-intercepts, minus 2, 0, and 2, 0, right? And these guys give me x equals to minus 3, x equals to 3 vertical asymptotes of the graph. All right? That's what's going to happen with those. So step 3, I draw my number line. I'm going to draw it over here because I want to put my graph under the number line. So you can, if you draw your graph right under the number line, then that makes things nice and pretty. I'm starting to, well, I regret my numbering here. I wish I'd made number 1 like number 3 instead. If we switch number 1 and number 3, I think it might be a better choice. But I made my bed, now I have to lie in it. Let's see here. So here we go. Here's my number line. What are my critical numbers? You got yourself a minus 3, a minus 2, a 2, and a 3, all right? Not x here, but f of x. So how about the signs? I want to add pluses and minuses to that, right? So what do you guys think I should do? Plug in a value, right? Or think about a large number if you like. If you plug in, say, what, 4, that would put us on the rightmost case, right? So if I plug in 4 into this, I get 6, I get 2, I get 7, I get 1. Those are all positive numbers, right? Plus, 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 plug in 4. So you can see we start out positive, yeah? And then the sign flip theorem still works, right? You still can just look for like the total number of times the factor appears, and that's going to be its order. So each one of these only appears once, which means that at every critical number we flip signs. So we go plus, plus, minus, minus, plus, 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 minus, minus, plus, plus. All right, like that. You know, the other thing, to make a graph better, what can we do? We can just plug in a point, right? If we just add a point to the graph, it's sometimes helpful. But I think I have most of what I need now. So my y-axis is in the middle of minus 2 and 2. And the graph is going to look something like the following. So I'm going to take mine. Let's see, my vertical asymptotes are where? At -3 and 3, right? So that puts dotted lines here and here, right? I have x-intercepts of -2. Oops. Well, anyway, my scaling isn't quite right, but you get the idea. -2 and 2, these are my x-intercepts, right? And so that, and what else do I know? What's my y-intercept? 1, right? So I guess that's something like this if I use the same scale. That's my horizontal asymptote. The function's getting drug into that eventually. All right, so yeah, here we go. This is -2, 2, and again the vertical asymptotes are 3. And -3. Okay, so here we go. We're negative on this, right? So it's got to do something like this. It's got to go like that. And then it eventually goes positive up to, you know, it's like that, right? So it's got to do something like that. Because it's going to -infinity as you're approaching the x equals -3 asymptote from the right. And it's going to +infinity as you're approaching the x equals to 3 vertical asymptote from the left, like that. And then on the other side, it's positive, but it's stupidly large, so it's like this. And then that horizontal asymptote of 1 means that you're drifting into that y equals 1. And over here, oh man. Oh guys, is that right? Look, can I even follow my own sign chart? So you guys tell me. Am I wrong? I'm wrong, right? So what did I do wrong? What have I ignored? We have an x-intercept at what? 2, right? So I have to do what? I have to connect the dots. I have to go through that. I have to go through there, right? So I have to go through there like that. And I go down, 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 down like this. So this right here was a typo. Okay. So we should erase that. That's not where it's supposed to go. All right. So we have to follow the sign chart. Yeah. We should be like positive where it's positive. We should be negative where it's negative, and we have to approach wherever we have a vertical asymptote. You're either going way, way up or way, way down, depending on whether it's positive or negative. All right. And if you're going from plus to minus or from minus to plus, you're going to have one that's going way up and one that's going way down. And then we also drift towards the horizontal asymptote eventually. So there you go. That's the graph right there. Now, if you wanted to make it better, what could you do? You could like figure out where the I don't know if this could be totally off. Like I really don't know exactly where this hump is. My intuition is by the symmetry of the problem, it does have like the sort of the top of the middle hump at x equal to 0. And that point is going to be, if you plug in 0 into the function, what is that? You get what, 4/9 if you plug in 0? So I think if I was more careful, it should be more like this. But you know, now I'm just fussing. We can always be a little bit more picky in terms of, you know, the graph being accurate. So, although it's hideous. Oh, it's hideous. Let's see here. So that is 4/9, which is, by the way, f of 0. All right, let's do another example. If you guys don't mind, I'm going to erase the algorithm because, well, I shouldn't yet. Can I erase this? think we've reached the time of the semester I need to watch my eraser. Let's see here. Example, oh no, I've forgotten. 4, 5, 6, right? So example 6, here's another one. Let's graph y equals to f of x equal to, here we go, x squared times x minus 2 over x squared minus 4 times x minus, let's say, 8 squared. There we go.